Hello and welcome back to the Rice Robotics Club Robo-Tutorial. In this video, we'll be taking our complete design, as shown here, making some minor adjustments so that it'll actually work better once you print out all the parts and you assemble it to actually build your robot. So, whenever we initially designed this arm, we were constrained by the torque that can be provided by this servo, right? So, or not this servo, sorry, this servo over here. So this servo has to put enough torque to support the weight of link 1, the weight of link 2, and the sensor at the end. So it turns out whenever I actually built this version of the arm, the links were too long and too heavy, and this servo can't handle it. So it just, whenever it tries to lift the arm, it just falls back down. And so we need to reduce the torque that we're requiring of this servo, and we're going to do that by making these links lighter and shorter. So we're going to start by making some small adjustments to both link 1 and link 2 to make the arm actually functional once you try to assemble it. So navigate to the link 1 part. And we need to open the sketch that's affiliated with the link 1 body. Hopefully you were naming your features and now we can find it easily. So we need to edit this sketch. Looks like this. So first thing we're going to do is make this shorter. So we're going to change this dimension from 108.8 to 80. And then we're also going to change the diameter of this circle from 20 millimeters to 15 millimeters. So this already reduces the size and the length, or both the weight and the length of this link quite a bit, but we can do even more by adding a cutout here, because this is a non-critical area, so we can just remove some material here and it'll further decrease that weight. So we're going to start by drawing a line here somewhere, okay? Escape the line. Now we're going to use a relation to make this line parallel to this straight edge, okay? And then we're going to define a parallel distance between these two lines to be 6 millimeters. So we need a dimension of both lines. This distance is going to be 6 millimeters. Okay, now we want to mirror this onto the bottom half of the link. To do that, we need to find the plane that's dividing the link in this direction horizontally. Probably going to be, it looks like it's the front plane. So choose the mirror tool. We're going to mirror about this line and mirror this diagonal line. Okay, and now I need to cap it at the ends. So we're going to add vertical lines that connect these two diagonal lines. Okay. Now we need 2 more dimensions to fully define this sketch. First, we're going to define a width for this cutout, or a length for this cutout, as 50 millimeters. And then we need a dimension to fully define its position. And that one is going to be an 18 millimeter dimension between this close edge and the origin here, okay? And with that dimension, the sketch is fully defined, and when we recalculate the model, we see that we have a shorter link that also has a cutout. This will significantly reduce the torque that we need from that servo. So this is great. Bad news is it introduces a problem, right? So we've decreased the length of link 1. For one thing, it's probably going to mess up our assembly. Let's see if the assembly still works. Okay, now the assembly is fine, but now that we've changed the length of link 1, the length of the belt that goes around these pulleys has also changed. And that might not sound like a big deal, like, okay, let's just change the length of the belt. But remember that we changed the length of the belt by scaling down our current model. And if we scale down our current model, we have to scale these pulleys by the same factor. So this could be very annoying. So we need to find a way of fixing this issue that is not overly complicated. So the way we're going to do it is we're going to use what's called a variable studio. And we're going to develop a method of automatically updating that belt and pulley size as we change the length of this link 1. Okay, so let me pull up a sketch that kind of demonstrates what I'm talking about. Okay, so this is the calculation here. This is how we derive the equation we need to determine what that scale factor should be. So we use the length of link 1 on these straight edges. In this case, it's still 80 millimeters. We also need to know the diameter of the pulley. And if we get 80 millimeters times 2 plus the circumference of one of these pulleys, that's the total belt length that we want to achieve. Okay, that's shown here. So this is 2 times the straight length plus the circumference of one pulley. That should be the total length of the belt. Okay? And we can also say using the initial diameter, the diameter of the pulley after it's scaled is equal to the relation ratio, or that scale factor, times the initial diameter. Same for the length of the belt. It's related to the initial length times that ratio. So we can plug those in into this equation and then rearrange and solve for R, right? And we get this formula here. So it's going to be 2 times the length of link 1 divided by the original length of the belt minus the original circumference of the pulley. Okay? So all that's to say we now have an equation that we can convert a length of link 1 to the appropriate ratio to scale both the pulleys and the timing belt. So how do we actually implement this in Onshape? We're going to use what's called a variable studio. So outside of all of our folders, we're going to hit plus in the file select. We're going to create a variable studio. So in a variable studio, you can define any number of variables that you want, and we can use these variables inside of our parts to specify certain dimensions. So for example, you could use one variable to define 5 different lengths across all of your parts. If you change the variable in the variable studio, all 5 of those dimensions will update. So this is a very powerful tool, and we're going to use it in this case to automatically rescale our belts as we need to. So to do this, we're going to define several different variables, 4 total. First, link 1 length, then starting belt length, starting pulley diameter, and then the scale factor that's going to be calculated from those other values. So these 3 will be the length values. The scale factor should be dimensionless, so we're just going to change it to any. Okay. Now link 1 length, we've defined it just now. It's 80 millimeters. Okay. And then from McMaster, when we imported the pulley and the timing belt files, we could get the initial length and the initial diameter for those. I just have those ready for you here. Initial length of the belt is 375 millimeters, and the initial diameter of the pulley is going to be 38.2 millimeters. Okay. Now we have all 3 of these quantities that we need. We're going to apply this formula and use that to calculate our scale factor. So you can use variables that you've already defined to define the value of other variables, which is pretty cool. So how it's going to work is 2 times, and whenever you're going to use a variable to define a dimension or define another variable, you always start with the hashtag, and then you type the variable name. So we're going to do 2 times this link 1 length. So we're going to go 2 times hashtag link 1 length. And we're going to divide by the starting belt length minus pi, which I think you can get just with this. Yes, so it's already defined here, so just type pi in all caps, and it will work for you there, times hashtag starting pulley diameter. And now that should be our formula. Should have closed the parentheses, hit enter. Yes, this is the scale factor we need. So now we've calculated the appropriate scale factor, and now we just need to actually apply these variables to our models so that they automatically update as needed. So first, we're going to go to link 1. We're going to edit that link 1 body sketch. And this time, instead of typing this value, we want to reference a variable to define this dimension. So it's going to be hashtag link 1 length that we just defined. And it's still 80, but in this case, if we change that variable in the variable studio, it'll automatically update this model. Now we need to go to everywhere where we scale a pulley or a timing belt, okay? So first in pulley, let's go to this transform feature and edit it. Instead of providing the scale factor directly, we're going to use a variable, hashtag scale factor. You'll see it gets smaller because we require a smaller pulley for our new design. You can see there's some issues with these holes. We'll be back to fix that in just a second. The timing belts, we're going to do the exact same thing with the transform feature here. Okay. Belt also shrinks. And then remember, we also have a pulley as part of link 2, so we need to make sure to update that as well. We're going to edit, transform feature, hashtag scale factor, and that one shrinks as well. And this also introduces some issues with the holes. We'll be back to fix that in just a second. So we'll start with the pulley and make some fixes for this. One thing is these holes, instead of cutting into the main body of the pulley, now they cut through the teeth, and that causes some issues. And so we need to change the distance of these holes from the center. So we're going to edit. It's the sketch affiliated with the servo horn mounting holes. Okay, we're gonna edit. And now we want to basically divide the distance separating these two holes by 2. Which is just going to mean we're going to reduce this dimension by 2.5 millimeters. The math on that holds up. There's 5 millimeters between these two dimensions, so we're just going to subtract 2.5. That gives us 8.55 millimeters. And now they're much closer to each other, and they will no longer cut into the teeth of the pulley, which is good. Okay. Another issue we're going to run into is with link 2. These holes are now just in the side of this part, and that's not going to be useful for mounting the sensor holder or the sensor mount. So to do that, we're going to edit the sketch affiliated with the sensor mounting holes. Okay, it's probably the last feature in your part. And we're going to change this separation from 13 millimeters to 9 millimeters. Okay. That will improve, make sure all those holes are actually going through the body. And now this can also be made much shorter because this diameter has been decreased. It'll also just reduce the torque needed by that first servo, which is a win. So we're going to go edit link to body. We're going to change this length from 80 millimeters to 50 millimeters. Okay. And now it's much lighter and reduces the torque it's putting on that servo. Cool. We have a few more things to fix here. Link 1 has an issue. If you look at the top, this cutout is no longer here, which introduces errors in this feature as well, where you have the servo horn mounting holes. The reason for that is, remember, we used a derived feature to pull the sketch that defines like the servo horn profile from the pulley. I'll remind you what that looks like. Should be here, this sketch. We pulled this sketch and added it to link 1 using a derived feature. But now that we've changed the size of the pulley, we go look at this cutout. You can see it's still extruding, but it's not intersecting the model, and that's because basically what's happened is the sketch has changed its position relative to the origin. So it's a little bit complicated, but basically we need to update the position of that derived feature so that we actually get this cut out like we want. So just like we did before, if you remember, we need the distance from the sketch plane, the sketch, to the origin, and that tells us how much to shift our derived feature by. So select this face. We need to show the origin and select it. Go to the measure tool, and we just want the distance in the Z direction. In this case, it's 7.6 millimeters. So we're going to edit link 1. We're going to exit this feature, edit the derived feature. And remember, we defined the position of this sketch by editing this make connector. So here we're going to change this offset distance from 10.332 to 7.6 millimeters, that value we just measured. And now if we accept all these details, we see the cutout is once again in the rod. However, you can see this no longer goes to the edge. This is because the pulley and the end of this rod used to be either the same diameter or the pulley used to be larger, but now that the pulley has become smaller, this cutout doesn't go all the way across the rod. And so to do this, we need to go actually edit the sketch in the pulley, and we need to make it larger, basically, make it extend further out from the pulley. So we can do this pretty easily. I'll hide this again, but then we'll edit it. Okay, so basically we need to make this circle on the outside larger. And right now it's just defined to match the diameter of the pulley, but we need to change that. So start by selecting all of the arcs that make up this circle and deleting them, okay? And then all of these points where these lines intersect the circle, we need to remove the relation that holds that point there, which is this coincident relation. So for all of these points, click the point, click the coincident relation and delete it. That all the way around. This makes our sketch undefined again, which means we can shift it outward like we're wanting to do. Okay, select the coincident relation. Okay, now we need a new circle of the correct size to tie this sketch to. So to do this, let's see what the diameter of this rod is. It's 30 millimeters. We go back to the pulley sketch. We're going to draw a 30 millimeter circle out here. Okay. Use a dimension to specify a diameter of 30 millimeters. Okay, and now we're just going to drag all these lines like we've done before to the circumference of this circle, and it will fully define the sketch. Okay. Very similar to what we've done before, but now we're just making it a little bit larger so that it still works with our link 1 design. Final thing is we want to eliminate these larger arcs because they don't actually contribute to our profile. So before we convert those to construction geometry, this time we're just going to trim them because it's easier. And in this case, it doesn't change our result. Finalize this sketch. And now this feature looks exactly the same, right? It didn't change anything because all of the additional area we're cutting is just empty space for the pulley. However, if we look at link 1, we now see that the cutout spreads out all the way across the rod just like it did before. So this is good. This means we've fixed the cutout. And now let's see if we do need to update at least one other part. The thing is, whenever you start making changes to your CAD that you didn't intend on making, oftentimes you'll realize it had unintended consequences in other parts, and you have to go fix all of those things. So it's just what we have to do. In this case, the final thing we need to do is update the holes in the ultrasonic and the sensor mount. And the reason for that is if we look at this assembly, the holes will no longer line up because we moved the holes in link 2. So the middle hole still lines up because it's centered, but then these other ones do not. So we need to shift the circles on the sensor mount to make everything line up again. So we're going to go into the sensor CAD. We're going to edit. You can right click this feature and it'll show both the feature that you can edit and the sketch. So we're just going to edit the sketch. And remember, we changed this separation distance from 13 millimeters to 9 millimeters. Okay. And now holes are much closer together. If we go back to the assembly, these holes should now line up. Once it updates, it takes a moment. There it is. And now the holes are aligned again. So, great. Let's make sure our assembly isn't broken in any way. Oftentimes when you change parts that make up assemblies, things can break. And you might have to go hunt down those problems, make sure all the mates and everything are working correctly. But in this case, the assembly looks good. And so now we've created a much lighter and shorter version of our arm that is still functional. And it should, at least in my testing, be much more, operate much better with the limited torque provided by this servo. So we're good. So that's like the major design alterations we need to make sure this is a viable design. However, there's another component in that you need to make sure that you prepare your parts for 3D printing. And the biggest problem that you're going to face whenever 3D printing CAD models that you've designed are the size of the holes, okay? So we've designed all of these parts with holes that are the exact size we want for various bolts and to fit other components within them. But now, whenever you actually 3D print these things, all of those holes are going to be slightly smaller than how you define them in CAD. And that's just because 3D printing is only so accurate and it has this tendency to print these holes smaller than what we designed in CAD. Just super annoying, but we need to accommodate for that somehow. So we have to go around, look at all of the holes and make them slightly bigger so that whenever we print them, they'll be approximately the size that we intended when we first designed the arm. So this can be a tedious process, but it's something we have to deal with if we're going to be 3D printing our parts. So I'll show you some of the common approaches to dealing with this problem. So first, maybe we should run through the parts and see what all needs tolerances, okay? So these holes are going to require tolerances because they have bolts, and those are the bolts that hold the base motor in place. These holes are just for wire management, so they don't need to be too precise. So you won't need tolerancing on them. The drive gear, this part here, will need tolerancing because right now well, actually, I'm not sure if it is. Oh, no, it is. It's the exact right size to fit that motor shaft. but if we print it, then it's going to be slightly too small and it won't fit. So you need to do a small offset. You need to make this a little bit bigger. So I can show you how that would be done. I don't know exactly what offset would be appropriate, but I think I remember what I did in my design. So we have this, but we need to create a version of it that's slightly bigger so that it will print successfully. So the way I would approach this is select all of these edges, convert them to construction, and then do an offset. Okay, oh, that's a mirror. Do an offset of these entities. Make sure it's going outward. It's going to be maybe like a 0.2 millimeter offset. What does that look like? That looks reasonable. These tolerances aren't going to be huge. It's just going to be a small adjustment so that you can be confident that the holes will be the right size when you print them. Okay, so this offset looks okay. Now we need to convert the ones that we actually want to define the geometry, which are the offset version, and change them from construction back to normal geometry. Hit the check mark. And now this hole is very slightly bigger. You might not be able to notice, but now we can have much more confidence that it will fit the motor shaft whenever we actually print out the part. Okay? So that's basically the approach you're going to take with all of these holes. Okay, so let's take a look at the base plate. These holes, you may need to make them slightly bigger, but as long as the holes in the gear and the holes in the base plate are the same size, you're probably doing well. Same with these holes here that are used to mount the servo to the base plate. Oh, they have a whole other issue that I'll return to in a second to show you how to deal with that. We'll look at the pulley. These are going to require an offset. This link cutout is already offset enough so that it won't require any adjustment. So that's nice, but these will need to be offset. The timing belt is fine. Link 1. So this cutout in link 1 is going to require an offset because there's a tendency for the holes to be too small when you 3D print. And also this part, whenever we print it, the rod itself is probably going to be slightly larger than we designed in CAD, just due to inaccuracies of printing. So we need to make sure there's enough of an offset. I'll hide the rod here. Enough of an offset in this cutout so that we can have confidence that it'll be somewhat accurate whenever we 3D print it. So that would follow a very similar approach to what I did with the drive gear. And I can't really walk through and do all these things because there's a lot of them to do, and the amount of tolerance you need is going to change a lot between different printers and different sets of printer settings. So you really need to do this testing for yourself to figure out what the size of different holes need to be. So this hole is where this part of link 1 passes through. So you can leave this part of link 1 the same size, but you will need to make this hole a little bit bigger to make sure that it will fit that part of link 1. These holes you can also adjust, but I don't think we've really designed these for any specific bolts. So first, I would go to the ODEC, go to the bolt cabinets, figure out what bolts are like readily available and you can use, and then design these holes to be slightly larger than the diameter of those bolts. Okay. I don't want to recommend to like everyone that's doing this tutorial to use the exact same bolt size because then they'll never be available. Go to the ODEC, find one that's reasonable and very available, and design around that. Okay. And pretty much the same here. You'll need another offset for these, just like these, just to make sure that the bolt that you select is going to pass through both. So there's a lot to be done here, a lot of holes to experiment with. So there's going to be a benefit to whenever you're choosing what bolts you want to use, you probably want to choose as few types as possible. Okay. So you may want to try and use the same bolts to, for example, attach the sensor mount to link 2 as you use to attach the base motor to the base hub here. That way you have to do less testing. How do you actually conduct that testing? You do it by using a whole test piece, I would call it. It's basically a little piece that you'll 3D print that has holes of a bunch of different sizes, and then you can test all of those different hole sizes and see which one is the best for your bolt. So I'll show you an example that I made the other day. Yeah, so it's a very simple thing to CAD up here. You used to have like a small block, and then you have a hole. I would start with the diameter of my bolt. So this is, I believe, designed for a number 0 type bolt, which has this diameter. And then I would slowly increment that, making it slightly larger with each hole, and then find which of these holes works best for my design. So design a piece like this, a small extruded piece with a couple different hole sizes in it, print it, and this is a very small piece, so it should only take a few minutes to print. Test and figure out which hole size is the best for this specific bolt. Update all of the CAD models. For example, if you're doing this for the bolts that will hold the motor into the base hub, then you should figure out, run a hole test for whatever kind of bolts you're going to use for that application. Figure out the exact diameter that works best for your design, and then update these holes before you print. And then once you've decided that, if possible, print on the same printer just to minimize any randomness or inaccuracy that could lead to your design not working. Or just the bare minimum you should do is make sure that you're using the same print settings. Same printer is ideal because I'm not even aware of all the factors that influence the printing accuracy. Um, but just try and keep the conditions exactly the same whenever you print your next version so that those holes are as accurate as possible. Okay, so this is my suggestion for how to hone those hole sizes quickly, is to print a few of these test pieces. It doesn't take very long, and it's a quick way to figure out a pretty precise diameter for your various hole sizes. But there's another problem with holes, unfortunately, when 3D printing, which is vertical holes. So most of the holes in this design are horizontal, which means the 3D printer is going to print in this orientation. So it's going to print a bunch of very thin layers on top of each other, and it's going to print this hole, I guess all at once would be a good way to say it. You're not building up this hole over time, but if you look at a vertical hole like this one, you're going to be printing layers and building up over time. And what that leads to find a picture of this, is whenever you reach the top of the hole, it's just going to cut it off. It's going to flatten it out, and your bolt won't fit through if you don't make some adjustment. So to fix this, either you can just drill out the hole, like it'll almost be the entire hole once the print is complete. So you can just, run a properly sized drill bit through it, and it'll open up that hole. Or if your hole is very small and we don't have a drill bit that works that's small enough for it, or if it's hard to access that hole with a drill, you can use some other geometry that allows for some flexibility in the size of that hole. Or what I like to do is this teardrop design, where it prints all of this part of the hole fine, and then at some point you reach a straight line that goes up in this teardrop shape, and it actually never cuts off the hole like this. It definitely give you the full area needed for that bolt area. So this is the approach I would take. Like I said, there aren't many vertical holes in this design, but both of these holes, this hole and the one on this side, have this issue. So we can edit this. I can show you how to add that teardrop geometry. So I'm just going to edit the first servo mounting hole. Normal. This works. So basically what you need to do is you need to add a line. It's going to be coincident and tangent to the circle. And then it needs to be, I'm just going to save this line, it needs to be vertically aligned with the origin. I believe that's the origin. No, it's not. The origin's down here. It needs to be vertically aligned with the origin. Okay. So go to the relation menu, select vertical. Make this point vertical to, I selected the wrong point, let's see. Vertical to, that's annoying. Origin, okay. That's not, oh, we're reoriented. So vertical is actually in the Z direction, so we have to make it horizontal, which is very confusing. That happens sometimes. Horizontal to the origin. And then we just need to define the vertical distance from the center of this hole to the top of this teardrop shape. So to do that, I'm just going to use, let's see what I put in the tutorial. A vertical distance of 1.4 millimeters. This is pretty flexible. It's not too precise what you do up here, just as long as it's a reasonable gap up here so that you definitely get this whole area. It's all good. And then we need to mirror this line about the plane that divides this vertically, which is here. So we're going to mirror about this line, like this. And then the last thing we need to do is trim away this extra piece of the arc so that our teardrop profile is complete. So I'm just going to select the trim tool and drag over this section of the arc, and now the teardrop is complete. So if we finalize that sketch, can't see it from this angle. Coming up front, we now have a teardrop shaped hole that will help to have better quality on some of these vertically printed holes. So just keep that in mind as well. This is something you might have to deal with because if we don't add this additional geometry up here, it may just print round all the way up here and then just suddenly flatten out at the top, which can introduce some issues. So keep that in mind. You should probably do it for this hole as well, but I've already showed you the method, so just make sure to apply it to that hole as well, and then we'll be good to go. So this whole process of tolerancing can be really annoying. There's certain workarounds, like oftentimes the hole size needed for these bolts can be pretty flexible. You can usually find a bolt that works for your application. Also, a lot of the times, like I said, you can just use a drill if the hole is a little bit too small, you can use a drill bit of similar size to make it just slightly larger and make your design work. Just know that it's going to be an iterative process. You're going to have to try and probably fail a few times before you get a design that totally works together. Just persevere, and if you're having a lot of trouble, just reach out to some other robotics members, or you can reach out to me through the Slack, or if you see me around the ODEC, that's fine. Um, this is a kind of a fact of 3D printing that you have to do some iteration to get the design to be totally cohesive. So I hope that you'll push through the struggle of tolerancing, and you'll get your design working. So thanks for watching. I'll see you in the next part of the tutorial.